In section 20.3, we are going to look at the force on a current carrying wire placed in an external magnetic field. So first I want to point out that this wire, current carrying wire, is being placed in an external magnetic field that we are assuming to be constant, such as maybe what we would see between the two poles of a horseshoe magnet, right? So we're assuming for the length of the wire, the magnetic field strength is more or less constant. And if you recall from the last section, we learned that a current carrying wire produces its own magnetic field in concentric circles around the wire. Now, this magnetic field produced by the current carrying wire is not constant. Remember, it is strongest near the surface of the wire and gets progressively weaker as it goes out. But the reason there is a force on this wire is because the current generates its own magnetic field. Okay, so when we place the current carrying wire in an external magnetic field, there's an interaction between these fields. Now, this is an algebra-based class, so our method and the method of this textbook has been to first we calculate the magnitude of a vector, and then we conceptually determine the direction. But in this case, I want to point out that this equation for the force on a current carrying wire in a magnetic field, your current, your magnetic field, and your resultant force are all vectors, right? But in this equation, we're talking about the magnitude of those vectors. Now, the length of the wire is a scalar, but this equation is the magnitude of a vector product. So if you have happened to have had vector calculus, this will look familiar. But I point this out, two reasons. One, a property of a vector product is it gives us back a vector, and the resultant vector is perpendicular to the two vectors that we are taking the cross product of. In this case, current and magnetic field. So the other thing to remember, and this becomes important when you are determining the direction of the resultant force vector, is I cross B does not equal B cross I. So when you do the right-hand rule to determine which direction the resultant force is, I find it easiest to use the three-finger method. So our pointer finger points in the direction of the first vector, in this case current. Our middle finger points in the direction of the magnetic field, and then our thumb will point in the direction of the resultant force vector. So in order to do this, if we go by this diagram and say our current is going in this direction, okay? So, and our magnetic field is going to the right. So in order to be able to do that, I point my first finger in the direction of the current, my middle finger in the direction of the magnetic field. To be able to do that, my thumb must be pointing down, right? So my resultant force is into the plane of the page, and we represent that by a circle with an X through it. Okay. Now, the force on a current carrying wire is maximum when our current is perpendicular to our magnetic field, or when theta equals 90 degrees. So this is because sine theta of 90, or sine 90 degrees, is equal to 1, so this part goes away. The same thing happens for negative 90 degrees. So if the current, we're going in the opposite direction but still perpendicular to I, sine negative 90 gives negative 1. However, remember, we are talking about a magnitude with this equation, so we're going to ignore that negative sign and determine our direction conceptually using the right-hand rule. So I wanted to do this example problem. So problem 1 in the end of chapter questions. Let's run through this. Problem 1 asks, what is the force per meter length on a straight wire carrying a 6.4 amp current when perpendicular to a 0.9 Tesla uniform magnetic field? And B, what if the angle between the wire and field is 35 degrees? So, first of all, we have the situation where the force is going to be a maximum. And so that theta is going to be equal to 90 degrees, so sine theta is going to be 1. So we can use the maximum form of the equation, which is our maximum force is equal to current, the magnitude of current, times the length of the wire, times the strength of the magnetic field. Okay, but we want force per meter of length, so we're going to divide out by L. So F per L is going to be equal to the magnitude of our current times the magnitude of the magnetic field, which is just 6.4 amps times 0.9 Tesla, and we get something like 5.8 newtons per meter. Right? So, can we determine the direction? So no, because not enough information is given. So we're not given a direction of current or a direction of the magnetic field. But let's say, for the sake of argument, that we have this magnetic field that is pointing to the right, and we have a current carrying wire. So let's look at the situation where our current, we're going up. So I is going up and B is going to the right. Okay, so using our right hand, again, in order to point our first finger in the direction of I, up, and our middle finger in the direction of B, then our thumb has to be pointing down. So our resultant force would be into the plane of the page. So let's say our current is going down and our magnetic field is still going to the right. In this case, this is a little hard to do, but we need our first finger to point in the direction of the current and our middle finger to point in the direction of the magnetic field. And in order to do that, our thumb must be pointing straight up. So in this situation, if the current were going down, then our resultant force would be out of the plane of the page. So for part B, we want to know, what if the angle between the wire and field is 35 degrees? So again, we use this equation. Force is equal to IL times the strength of my magnetic field times sine theta. So same procedure, we have 6.4 amp current, and we're dividing out by the length of the wire, which will give us force per unit per meter of length of a straight wire. Okay, so we have current times the strength of the magnetic field times sine of 35 degrees, which is going to give us approximately 3.3 newtons per meter. Now, I want to give you one more scenario. What if our current carrying wire is parallel to our magnetic field? So we have a magnetic field that is going this direction. And we have a wire here. Say it's going to the right. Okay, so if the current is parallel to the magnetic field, then our angle theta equals 0. So if theta equals 0, then ILB sine 0, and that's the theta, 0 is going to be equal to 0. So if our current is in parallel or anti-parallel, so if theta is 0 or 180 degrees from the direction of our current, so if I is parallel or anti-parallel to the direction of the magnetic field, then our force on the wire is 0. Stay tuned for more on magnetic fields.